Welcome to the Architectures of Intelligence, a blueprint for the generative AI revolution. We will trace the evolution from rule-based systems to the transformer architecture and explore the factors driving this revolution now. First, let's establish a clear framework. Artificial intelligence is a broad field. Within it, we find machine learning, which uses data to make predictions. Deep learning is a subfield of ML, utilizing multi-layered neural networks. Neural networks are the backbone, inspired by the human brain. AI development began with two foundational philosophies: symbolic AI and deep learning. Symbolic AI is rule-based, offering high transparency but low adaptability. Deep learning is a pattern recognizer, offering high adaptability but lower transparency, often called the black box problem. AI models are defined by their core mathematical task. Discriminative AI focuses on classification and prediction, separating data categories. Generative AI focuses on creation and simulation, learning the full patterns of the underlying data to generate new content. Before the current generative wave, the primary source of enterprise value came from predictive AI. This AI analyzes historical data to forecast outcomes and optimize resource use, driving competitive advantage in logistics, manufacturing, retail, and finance. The 2017 transformer architecture caused a revolution, enabling modern generative AI. Unlike older recurrent neural networks, which suffered from a sequential bottleneck, the transformer introduced massive parallelization, fundamentally changing how sequential data like text is processed. This leap was made possible by its core component, self-attention. The efficiency of the transformer comes from the self-attention mechanism, which weighs the importance of different words in an input sequence. However, processing all tokens at once created an order-blind trade-off. This required a compensatory mechanism, positional encoding, which restores sequential information, though early implementations limited the context window. Beyond language, the diffusion model now dominates high-fidelity image generation. Its core principle is counterintuitive. To create a perfect image, you must first learn how to destroy it. The forward process adds noise, and the reverse process iteratively denoises the image, generating a high-quality result. Performing the denoising process directly on high-resolution pixel data is computationally prohibitive. The latent diffusion model addresses this by using an encoder to compress the image into a smaller, lower-dimensional latent space. Cross-attention then links linguistic tokens from the text prompt to visual concepts within this space, guiding the image generation. Two leading text-to-image models, DALL-E2 and Stable Diffusion, illustrate different philosophies. DALL-E2 is proprietary, excelling at photorealism. Stable Diffusion is open source, offering greater flexibility and customization through its community-driven innovation. The performance of modern AI is governed by neural scaling laws. The Chinchilla revelation showed that optimal performance is achieved by scaling model size and training data in equal, proportional tandem. This proved that many massive models were significantly undertrained. AI models trained on raw data learn statistical patterns but lack human values. The crucial final step is alignment, achieved through reinforcement learning with human feedback, or RLHF. This transforms a raw predictive engine into a helpful and instruction-following assistant. Predictive and generative AI are distinct yet complementary paths to enterprise value. Predictive AI focuses on optimization and efficiency, thriving on proprietary, domain-specific data. Generative AI focuses on innovation and velocity, trained on public internet data to accelerate content creation and new forms of customer interaction. The path forward includes enduring architectural and ethical challenges. These include the, quote, black box nature of deep learning, the physical limit of the context window constraint, and the gap between broad knowledge and specialized expertise, requiring integration of public and proprietary data. The future is hybrid and explainable, converging the strengths of symbolic AI, deep learning, and scaled generative models. This trajectory leads to explainable generative AI systems that deliver both innovation and accountable, transparent utility.